Good afternoon, ladies and gentlemen, and we're happy to here to talk about the implementation synopsis of the Gluon project. And let me start with the business goals and design goals of Gluon itself. And Gluon is targeted for addressing the networking services and with extension about the new networking services on demand and to support multiple SDN controllers. And we'll have a quick development and deployment of new NFV Networking Services itself and to try things new fast and to fail fast of the services. And also we have a quick access to the different capabilities of different SDN controllers, and so that we have the multiple SDN controllers can be run simultaneously to support multiple different services on the back end, of course. And the ultimate goal is that Gluon will be able to work with Neutron simultaneously, so that all the happy users of current Neutron networking will be happy forever. And so let me introduce my colleague Tom Hambleton, and so he will give the more details about the implementation.
Okay, thank you, Ben. Okay, let's start with an overview of the Gluon architecture. The main component of the Gluon architecture is the networking API, and in Gluon terms, a networking API is a port provider for a specific network service. In the Gluon, we see that you should be able to support multiple networking APIs in one cloud environment, and each one of these APIs will provide ports for that particular networking API service. The main feature of Gluon is we make it very easy to generate these networking APIs. We have a framework that will take a specification file and generate most of the logic to implement this API. We call these APIs that are generated by our framework a Proton, so you'll see that term in the following slides. So a Proton is a networking API that's generated, provides a specific network service, and it'll provides ports that can be bound to VMs. Another concept behind Gluon is that the compute service, being Nova, doesn't really need to know about the networking service provided by that port. It just really needs to know that it wants to bind that port to a VM. So, so that's kind of a thing is when the VM wants, compute service needs to bind the port to the VM, it needs to know that that port bind request needs to be routed to the proper networking API. And so to make that happen, we have this bubble in the middle called Gluon, which is providing our port arbiter function. So what it maintains is a mapping of ports to the different networking API backends. And so the networking APIs, when you hit the networking APIs and you define your service and your port, the port is registered with the port arbiter so that when the bind request comes in, it will be routed properly. So during VM creation, you'll see the port bind comes to the Gluon, it routes to the right network API. The network API is then responsible for making sure that the backend, which will probably be an SDN controller, is configured properly to provide that networking service for that port. So we're going to show what we actually have in our repo. You can actually go out to the web and look in our GitHub, the OpenStack GitHub repo for Gluon. And the red objects here are the main components that we have. The Proton server is generated from a set of YAML files. We have an L3VPN modeled with our YAML files. And the Proton server, you can see the code for that. The port arbiter function we had to do a little differently. Originally, we were going to replace the networking plugin inside Nova and have the Gluon server, the port arbiter function, be a separate service and then route that to the individual Proton servers. They've deprecated that in Mitaka, so to get around that, we've created a plugin wrapper, a Gluon plugin wrapper that sits inside the Neutron server. We've overridden the port update and the port show methods, and that's where we actually do the port arbiter function. We can actually then look to see is this operation for a Gluon port, and if so, we'll forward it onto the proper Proton server. If not, we'll go ahead and let it go on to the core plugin to be processed by Neutron. The other thing to mention is the shim server, the shim layer actually, and that is responsible for configuring the SDN controller based on changes to the data model. And so I'll go into detail how that all plugs together next. So here's how you would actually use Gluon. So our Proton server here would have an L3, what we're showing in the marketplace has an L3VPN service available. So you would define your port, you define your network service, you attach that service to the port so it'd be ready to use by VM, and then you would use, the Proton server store that in persistency, and also stores it into an etcd key store value database. At this point, the shim layer doesn't have to act on it because the port's not really bound to anything. But now you actually want to use that port, so you use normal Nova mechanisms to create the VM and bind it to that port. That goes to Neutron server, and then the Gluon plugin wrapper will intercept that port update method. It'll check to see if this is a Gluon port. In this case it is, so it'll format a port bind request, REST call to the Proton server. And the Proton server then will update the database, push the information automatically back into etcd. Now the shim layer has to act on it. So this is a case of the shim layer is watching for changes into the data model presented by etcd, and it will appropriately configure the etcd backend for that port. I mean the new SDN backend for that port. Importantly, it also will store the VIF information back into etcd. This will be the VIF type and the VIF details. And then the Proton server actually waits for that to be updated, and then it sends its response back to the Neutron server and goes back to Nova. And this synchronization is actually important because the Nova needs the VIF information when it's creating the VM to actually get it plumbed properly on the hypervisor. Okay, so another, probably one of the main benefits or big features of Gluon is our model-driven API creation. In the Proton server, we don't actually generate code. When the Proton server is loading, it will parse these YAML files which define the API service. We actually have a model called the particle generator, which will then generate all of the classes needed to support the REST API. We use the Pecan framework with WSME for validation of our REST API. It generates all of the SQL Alchemy classes needed to store any updates to that API, to the API objects and to persistency. We also will, we don't have right now, but we will generate the Alembic migration code for that if we change the API spec. Also, there's the automatic synchronization to the etc backend is generated for you. And to exercise the API, we actually also generate a CLI, which would actually exercise the API, so it makes it really easy to test. Some of the future things we're thinking about is generating heat resources and potentially generate our API documentation as well. Okay. Another note is our backend synchronization. We don't use the traditional agent, the plugin agent with RabbitMQ mechanism that Neutron uses. We are using etcd to use a distributed key value store database. This is actually used in other things like Kubernetes does this to maintain configuration, so it's a pretty robust and scalable solution. So the way this works is that, as we said, as a Proton server receives API request, it'll push that and maintain that data model in etcd. So the shim layers will basically wait for changes in the etcd database, and as it sees changes, it'll determine, is this change for me? And if it is, it will then configure the SDN controller appropriate. And another benefit of this approach too is it lets us support multiple SDN controller backends in one Nova instance, right? So in our demo we're showing the marketplace, we actually have multiple vendors under one Nova, and each one of the vendors has separate shim layers controlling their particular hypervisor for that service. Okay. One last thing I'll talk about is the Proton server is designed with HA and load balancing in mind. We should be able to sit behind an HA proxy. We use a journal table and a common MySQL database to synchronize the backend updates to etcd. And it's important if you get multiple Proton servers, they could get out of sync. But so we use a journal file to synchronize the updates to etcd to maintain consistency. Okay, so that's pretty much all I have. So now I'm going to turn it over to Nicholas to give a quick demo.
Yeah, so I will do a short demo, which we just recorded very shortly before here, before this talk. So first of all, you see here on the right side, that is a VM, and that is actually pinging at the moment. You can see that. And I will show now here our first implementation. Our first Proton implementation is layer 3 VPN. And I will show here the very easy way to now connect the VPN port object So to connect a VPN and a port to create connectivity or to disable it again. So what you see here is now we are deleting this object, and you can see directly that the connectivity is not working anymore. And when we are bringing back the VPN port instance, then the connectivity comes back. So through that, we can now define the connectivity between a port and a VPN, layer 3 VPN, very generally. So in Neutron, for example, you can only do that per whole network. Here we can do it per port. The next thing I would like to show our client, which is completely created out of the YAML file. So we have here the base port, which shows all the attributes from the base, from our base port, which is the corresponding thing through a Neutron port. This is a layer 1 object now, so you don't need to have a Neutron network anymore. You can just have only a port without any definition of connectivity first, and then you can connect to any service, like for example a layer 3 VPN service. And another thing what we can as well show is the VPN port, the VPN list, where we can actually see the VPNs. We have now at the moment here 2 BGP VPNs, and they are actually up and running, and all the VMs which are in this VPN can reach each other very easily. Thanks.
Thank you. That's
Thank
all.
you.